Okay, now today we will discuss about the LR circuit. So first of all, what is the meaning of LR circuit? What we are doing here, in the circuit we are connecting a resistor and inductor with a DC source. Then we will see how the current in the circuit changes as a function of time. Because as we know, whenever inductor as well as resistor are connected in a circuit, or we can say when inductor basically is connected in a circuit, so the current will take some time to get stabilized. So before getting stabilized current, how the current vary in the circuit, that we are looking here. So there are two things here. One is the growth of current, another your decay of current. First we will discuss the growth of current. So see, growth of current means initial current was 0, now the current is increasing in the circuit. So this is our one resistor R and this is your inductor of self-inductance L. This is connected with a DC source with a switch S. Let the EMF of the source is your V and initially switch S is your open. So this is just one of the basic idea or one of the basic circuit I am considering here, and with this circuit just we are getting the idea how to make equation, then how to simplify our circuit here. See, at t is equal to 0, let at t is equal to 0, switch S close. Switch S close. Then see what will happen. So as soon as we are closing the switch, so it creates a potential difference in the circuit. Our EMF source will create a potential difference in the circuit. Because of the potential difference, charge starts flowing. Here this is your higher potential terminal, this is your lower potential terminal. So positive charge can go, basically electrons are flowing in this direction. So I is the current in the circuit at any time t, and that current you are changing here. So let at t is equal to t, I is the current in the circuit. I is the current and that is increasing. That is increasing, or we can say di by dt is greater than 0. So initial current in the circuit was 0. As soon as the switch is closed, current start increasing here. So as current increases here, the flux associated with the inductor, initial flux was 0. Now there is a flux and that flux continuously increases. So EMF develop here and polarity of the EMF is like that. It will opposes the flow of current. So induced EMF develop here and that written as L di by dt. So at t is equal to t, I is the current in the circuit and that is increasing. So di by dt is greater than 0. Now we can apply, so from Kirchhoff's law, at t is equal to t. Now we can apply Kirchhoff's law at t is equal to t. See, we are going like that. Suppose we are starting from here. So minus IR, then minus L di by dt plus V, that is 0. So this can be written as here L di by dt is equal to V minus IR, or we can say di by V minus IR. This is your dt by L. Now we can simplify here. So at t is equal to 0, when switch was open, that time current is your 0. At t is t, let current is your I. After that, we can simplify this. So further we can write like this. Minus 1 by R ln V minus IR by V, that is equal to your T by L. So from here V minus IR is equal to your V e to the power minus RT by L. So current value we can get right now. So I is equal to your V by R 1 minus e to the power minus RT by L. So this is the variation of current in the circuit. So if we are plotting a graph, how the current vary in the circuit, then we can say in that manner. So at t is equal to 0, when switch is about to close, there is no current here. After that, current here increasing like this. And finally, after long time, we can say current become a steady value, and then steady value is called your maximum value of current, and which is equal to your V by R. So this is the variation of current. So what are the main or certain point we can define or certain point we can note down while solving the such problem? So see the first point. First point is that at t is equal to 0. At t is equal to 0, the state is called your initial state. State we can say the initial state. See, at t is equal to 0, what we are looking here, I is equal to your 0. I is equal to 0. Now see from here, di by dt can be written as V by L e to the power minus RT by L. Now from here, we can see at t is equal to 0, di by dt or V by L, which is the maximum value. At this instant, if I am putting here, then what we are getting, E is equal to your V. So from that, we can say at initial state, whatever the applied voltage, that is across the inductor. So there is no potential drop across the resistor. So current in the circuit is 0, and that also coming from here. So conclusion is that at t is equal to 0, if there is no initial current in the branch, if there is no initial current in the circuit, then current across the branch in which inductor is connected, then current across the branch in which inductor is connected will be 0. So this is the outcome of the first point. It means if there is no current in the circuit initially, and even we have closed the switch, then there will be no current in that branch across which inductor is connected. So we can make our circuit like that. So then at t is equal to 0, that circuit can be equivalent like this. Since no current here, so although resistor is there, so this type of diagram can have at t is equal to 0. So in this manner, so it is equivalent to that type of diagram at t is equal to 0. Now come to the second point from here. Second point, at t is equal to infinity, or sometimes it is also called or at steady state, or it is also called after long time. All are the same meaning. See, at t is equal to infinity, if we are looking here, to this term will be 0. So current will be your V by R, and this term is 0, so di by dt is 0. So it gives us then di by dt is 0. So no potential difference across inductor. So there is maximum potential difference. There is maximum potential across resistance. So the current across the resistance will be maximum. So current across resistance will be maximum, and that in this case here that maximum current is coming here. Here I maximum comes here, V by R. Since di by dt is 0, no potential drop here, so our circuit, this circuit can be made like that. At t is equal to infinity, this is like this type of circuit here. So what can be done? We can simply replace inductor with a normal conducting wire. So current will be your I is equal to here, we can have V by R. So what we can do, at t is equal to infinity, we can make our inductor just like a wire, and at t is equal to 0, we can make our inductor as a closed open circuit. But all these conditions are valid only when there is no initial current in the circuit and switches was open. So as soon as switch is closed, then it will happen. So as soon as switch is closed, then initially it will happen, and after a long time, this is the condition will come. So that condition means when current become your maximum. So it does not mean there is no role of inductor. So inductor is there, and current through inductor is your constant, means there is no flux is changing. Flux is not changing, but inductor have stored energy. The energy stored by inductor can be given as half Li square. So right now inductor have energy, and that energy can be said as your equal to half Li square. Okay, now see the another conclusion from here. As I is equal to here V by R 1 minus e power minus RT by L. Now we can say here the unit and dimension of L by R is same as the dimension of time have, as the unit and dimension of time. So then the term L by R is defined as time constant. This term is defined as time constant. So tau is written as L by R, where tau is time constant. tau is time constant. So in terms of time constant, I is written as V by R 1 minus e or minus t by tau. So this is the another way by which we can define current. Now, how we are defining the time constant? See, in the expression of current, I is V by R 1 minus e power minus t by tau. When t is equal to tau, then I will come here V by R 1 minus e to the power minus 1. After substituting the value of e, what we found here, I is equal to 0.63 V by R, where V by R is our maximum current. So I is equal to 0.63 I maximum. So we can say the time constant is that time in which current in the circuit is there 63% of its maximum current during the growth of current in the circuit. So time constant is that time in which current in the circuit becomes 63% of its maximum current during growth of current in the circuit. During growth of current in the circuit. Likewise, we can define time constant. And now, in general, time constant can be written as tau is written as L by R equivalent. It's very important term here, R equivalent. Normally, I wrote here tau is equal to L by R, but in that circuit our only one resistor was there. But here if the number of resistors is there in the circuit, then how to calculate? So here R equivalent is the main point. So R equivalent is a equivalent resistance of circuit across the terminal of inductors, after replacing cell with a conducting wire. So how to calculate the R equivalent? So R equivalent, as here we have defined, R equivalent is the equivalent resistance of a circuit across the terminal of an inductor after replacing cell with a conducting wire. So just see one of the example, from that you may get better idea how to calculate the R equivalent. See, so here in this it is given, suppose this is our circuit. So question is that find the time constant of circuit. Time constant of circuit. So as per the time constant, L is defined as L by R equivalent. So what is the meaning of R equivalent? See again, as I wrote here, there. See the definition of that. In general, time constant here, L by R equivalent. So R equivalent, the equivalent resistance of the circuit across the terminal of an inductor. See, these are the terminals of inductor, we can see. So we would like to find the equivalent resistance across these 2 points, keeping the or battery. We can replace the battery with a conducting wire. So then our diagram can be set like this. This is your terminal of inductor. Across this we have to find, this is your R1, here cell with a battery, with a wire, this is R2, and next your R3, and this is your R4, like this, in this manner. Cell again we have replaced with a wire. So now see this. These two are in parallel. Then all the three will be your series. So R equivalent will be here R1 plus R2, R1 plus R2, and these two are in parallel. R3, R4 by R3 plus R4. So this is the value of R equivalent, and L already we are having. So time constant is written as L by R equivalent. So whatever the value of L given, that we can put here, and R equivalent we can write in this manner. So in this way we have to calculate the time constant for any of the given circuit. So this is a general idea about growth of current in LR circuit. Now come to the decay of current. Now come to the decay of current. In decay of current, it means current is already in the circuit. How the current is decreasing? See the one diagram here. So in this circuit, one inductor L, resistor R, and switch S1, S2 are given like this. So what is the condition given? Initially, switch S1 was closed and S2 was open for long time. This is given. Initially switch S1 was closed. S1 was closed means like this. S2 was remain open for a long time. So that is the condition of your growth of current. So as whatever we did in the previous case, that was the growth of current. In the growth of current we have found that when the switch was open, switch closed for a longer period of time, so steady state current will develop. Same thing will happen here also. S1 was here open, closed, S2 was open, so current will be set up here. And that current your maximum current, and that current can be said as I naught is equal to your V by R. So initially when switch S1 was closed and S2 was open for a long time, then current across inductor was, current across inductor is I naught V by R. Now at t is equal to 0, S1 open and S2 close. Switch S1 open and S2 close. So as soon as S1 open, S2 close, it means the circuit, from the circuit EMF source has been removed and S2 was closed. So since there is no EMF source remain, so to maintain the current, no device is available, so current start decreasing. So then the circuit can be set like this. At t is equal to 0, we can have this type of circuit diagram like this. This is your S2 switch which was closed here, and current is right now at T0, current is I0, which is V by R. Since there is no source of EMF is available, so that current cannot sustain for a longer time, it start decreasing. So current value decreases. The current decreases. So at T is equal to T, let at T is equal to T, let current in the circuit is I. Current in the circuit is I. In that case, see, R, this, and current in the circuit is I, and rate of change of current di by dt here less than 0 or negative. So EMF induced here, that EMF will try to maintain the same current, the polarity of like that, but here di by dt is negative, so that will be your minus L di by dt. Now we can apply again Kirchhoff law here. From Kirchhoff law we will get from Kirchhoff's law we can have minus IR minus L di by dt, which is 0. So di by I is equal to minus R by L into dt. Now we can simplify. T0 current your I0, T and T current your I. So this can be written as ln I by I0 here minus RT by L. So current in the circuit written as I0 e power minus RT by L. So current in the circuit you are exponentially decreasing. If we are making a graph here, we can have current graph like that in this manner. So this is called your decay of current. In fact, what is happening here, when the switch S1 was closed and S2 was open for a longer time, at that time current was your I0. In that time energy stored in the inductor was half L I0 square. But when we have removed the source of EMF, then that current start decreasing. So finally current becomes 0. At T infinity final current 0. So when current is 0, so whatever the energy is stored in the inductor, that energy come out in the form of heat through resistor. So this is the general theory or general idea about LR circuit. Now come to the some example. From that we can get much more better idea of the circuit. See. Now see, let's see one of the example based on your LR circuit. In this we are having like two coils or two inductors having self inductance L1 and L2. This manner. L1 and L2, these are the two coils. or two inductors we are having. Question is that, now see, at t is equal to 0, switch as closed, find the current across inductor L1 and L2 at steady state. This is the example, and now see how to solve this one. So what will happen, as soon as switch is closed, our EMF source create potential difference. Because of that, current here established. As soon as current start increasing, these your inductors opposes the change in flux, because initial flux or initial current was 0, so initial flux was 0. Right now, since current here increases, they are opposing. So let at any instant, if I is the current here, so in this current can be set I1, here current here I2. This is the condition here. So after some time, when current get stabilized, at that time, as I told you, inductor act as just like a wire. So first of all, at t is equal to t, here EMF will develop. See, L1 di1 by dt, and here your EMF L2 di2 by dt, and these two are in parallel. So at t is equal to t, we can have L1 di1 by dt is equal to your L2 di2 by dt. From that we can have an idea, L1 I1 is equal to L2 I2. This is the one equation, and this equation your independent of time. It is your independent of time. It means this relation is valid for all time, either steady state or initial state. So L1 I1 is equal to L2 I2. Now, at t is equal to infinity, when current becomes your completely stabilized, at that time our circuit can be made like this. As I said, the inductor act just like a wire. So here R is the resistance and V is the EMF, I is the current. Right now here current I1 and here I2. If we are applying Kirchhoff law, we will get I is equal to your V by R. So this is your second equation, I is equal to V by R, and from first law of Kirchhoff, since I is equal to I1 plus I2, from that we can have I1 is equal to your I into L2 by L1 plus L2, and I2 is equal to your I into L1 by L1 plus L2. We can substitute the value in I1, this expression here. So this is the final result, final conclusion. We can have this one. So this is the first example. Now see another example. We are having two inductor and two resistor like this, and these two are connected with a DC source along with the switch S and a galvanometer G, and the value of inductors are L1, L2, R1 and R2. Initially switch S was open. So as per the given diagram, initially switch S was open. At t is equal to 0, switch S close. So find the relation between inductance of inductors, and resistance of resistors. So that galvanometer always shows zero deflection. It means reading of galvanometer always shows 0. So galvanometer reading 0 will be only when these 2 points are at same potential. So let A and B are the 2 points and switch has been closed. So we can write galvanometer reading will be 0 when point A and B are at same potential. Point A and B must be at same potential. We can do one thing. At any time if I is the current here, let I1 here and I2 here. So since galvanometer there is no current, this is also I1, this is also I2. Now we can apply one Kirchhoff law here, another here. So as current is growing here, this is your positive and negative. This is also positive and negative. Here EMF is your L1 di1 by dt, and here EMF is also your same way L2 di2 by dt. So from first loop, let this is your loop number 1, this is your loop number 2. From first loop we can say minus L1 di1 by dt plus L2 di by dt, that is equal to 0. This gives us L1 I1 is equal to L2 I2. Let this is the first equation. Similarly, we can apply Kirchhoff law in the second loop. So from second loop, we can write minus I1 R1 plus I2 R2, that is 0. So this gives us R1 I1 is equal to your R2 I2 second equation. And now from first and second, from equation first and second, see, we will get the relation. L1 by R1 is equal to your L2 by R2. L1 by R1 is equal to L2 by R2, or we can say L1 by L2 is equal to R1 by R2. This is the relation between the self-inductance and resistance, so that the galvanometer always show zero deflection. This is the another example. Example number 3. In the given circuit diagram, initially switch S is open. Now at t is equal to 0, switch S close. Find the current in all branches at t is equal to 0, t is equal to t, and t is equal to infinity. This is the question here. The question is that we are having two resistor, one inductor, which is connected with this two resistor R1 and R2, one inductor. This is connected with a battery. Initially switch S was open. Now it is closed at t is equal to 0. So we have to find the current in all the branches. All branches means in this branch, in this, and in this branch. So see, just recall our previous RC circuit theory. In that theory we have derived, or we have proved that when there was no initial current, at t is equal to 0, inductor acts as an open circuit, and at t is equal to infinity, inductor acts as a simple wire. See, at t is equal to 0, our circuit diagram will be like this. As I told, T0 inductor acts as open like this. So if this is your 36 volt, here current your I, let current here your I1, here your I2. This is your 10 ohm and this is your 5 ohm. Now, since it is your close, this is your open circuit, so I2 is equal to 0. Now, so I, whatever current I is going here, so I is equal to I1. So I is equal to I1, and these two are series, so 10 plus 5, 15, 36, and this is 36 by 15 ampere. So this is the current at t is equal to 0. Now, at t is equal to infinity, if we have to make, that is called your steady state. In that case, see our diagram. As I told, or we have discussed already, that steady state inductor acts just like a wire. 36 volt, 10 ohm, 5 ohm, this is let I, here your I1, here your I2. Then see here, if I am now talking in this loop, here between these 2 points, those 2 points are the same points, there is no current because potential difference across the resistor here 0. So I2 is 0. If no current here, so all the current will go through here. Then I is equal to I1, and which is equal to your total resistance of the circuit will be your 10. So 36 by 10 or 3.6 ampere. So it is very easy way to make diagram at t0 and t infinity. Now we will find for t is equal to t, in that we have to some relation we have to find. Now see the diagram for t is equal to t. At t is equal to t, see the diagram here. Let here current your I, and this is let I1, this is your I2, and this is your 36 volt. Resistance value given here 10 ohm, 5 ohm, and self inductance given here 1 millihenry. Now, as current your grows here, so that will try to decrease the current, so your higher and lower potential, and the EMF value will be here L di1 by dt. Now we can simplify our equation. First, by Kirchhoff first law, I is equal to I1 plus I2. Another, we can use Kirchhoff second law in that loop, minus 10I minus 5I2 minus 10I minus 5I2 plus 36 is 0. This is your second equation, and here we can get a third equation. So minus L di1 by d2 di1 by dt, this is the here, and then plus 5I2 equal to 0. Now these three equations we can solve this one. So see, from first and second equation, from equation first and second, I1 value I can substitute in I1 plus I2. So here minus 10 I1 plus I2, so it becomes your minus 10 I1 minus 15 I2. So minus 10 I1 minus 15 I2 plus 36, this is 0. And then from the third equation, we can multiply 3 times. So minus 3L di1 by dt plus 15 I2, which is 0. And now we can add these two equations. When we are adding, minus 10 I1 plus 36 minus 3, L value 1 millihenry, 10 power minus 3 di1 by dt, which is equal to 0, and then we can simply integrate. So this can be written as 3 into 10 power minus 3 di1 by 36 minus 10 I1 is equal to dt, and integrate like this. So in that manner we can simplify. So at t is equal to 0, I1 value 0, at tt I1 is your I. So I1 is I1. Now we can get the value of I1. Just substitute the value of I1 and di1 by dt here, then we can get the I2 value. After that, I1 plus I2 equal to your I. So these are the different way or different type of problem based on your RL circuit which can be simplified.